All right, so welcome everyone to the non-commutative geometry seminar. Today we have Koen van den Dungen, so it's a pleasure to actually pronounce it in the correct way. Localisations and the Kasparov product in Unbounded KK-theory.
All right, thank you very much. So first of all, let me thank the organizers for the opportunity to speak here. I think it's one of the few small little positive side effects of the Corona pandemic that we have this nice international seminar going on now. So it's a pleasure to speak here. So the topic for today is basically revolves around Kucerovsky's theorem. So this is a theorem in the context of the Kasparov product in the unbounded picture of KK theory. So what this theorem basically does is if you have two unbounded Kasparov modules and you would like to compute their Kasparov product, and you have a candidate of what you think the product might be, then Kucerovsky's theorem gives you sufficient conditions which allows you to check whether your candidate is indeed the correct Kasparov product. So I want to briefly explain this today, and in particular I want to provide some more general versions of this theorem. So in particular I would like to increase the range of applications and examples that this theorem applies to. So that's what I will talk about today. So I think many people in the audience are quite familiar with KK theory, but I'm not sure if everyone is perfectly familiar with it. So I'll start with a brief introduction to KK theory. So I will throughout the talk consider three C-star algebras, A, B, C. A is also always assumed to be separable, and B and C are at least sigma unital. And then I consider a Kasparov module, a Kasparov AB module. So this consists of a Hilbert module, which is kind of like a generalization of a Hilbert space where you replace the scalars by some C-star algebra B. We consider a star homomorphism from the first C-star algebra A into the adjointable operators on E. So for a Hilbert space, all bounded operators are adjointable. For a Hilbert module, this is an additional assumption that we need to impose. And then most importantly, we consider an operator F. So usually we have set two gradings around, so we consider an odd operator. And we assume that for this operator F, these three operators that we write down here for any A in the algebra A, that these are compact operators. And then we consider these operators modulo an equivalence relation, which is called homotopy equivalence. So the equivalence classes modulo homotopy equivalence then form an abelian group. And this is the KK group of A and B. So here there are in particular two special cases. So if A is just the complex numbers, then this is just the usual K theory of the C-star algebra B. And if B is just the complex numbers, then this is the K homology of the algebra A. So this KK theory sort of combines both K theory and K homology into one unified bivariant theory. Yeah, so what I mentioned, I don't want to say too much about the equivalence relation, but in particular, if you have two operators whose difference is maybe not necessarily compact, but is what we refer to as locally compact. So if the difference is compact as soon as we multiply by an element in the algebra, then we call this locally compact. So if say F1 is a locally compact perturbation of F2, then they both define the same class in KK theory. So they are homotopy equivalent. Okay, so what's a typical example of a Kasparov module? So the example you can keep in the back of your head is elliptic zeroth order pseudo differential operators. So the operator F is an elliptic zeroth order pseudo differential operator. So more or less this first condition has to do with the ellipticity of F. The second is then saying that F is almost self-adjoint. And the third is saying that it's sort of a pseudo locality condition on these operators. Okay, so As I mentioned, locally compact perturbations define the same class. So if you think of zeroth order pseudo-differential operators, what are compact operators? Well, pseudo-differential operators with negative order are compact. So this is sort of telling us that the lower order part of the pseudo-differential operator doesn't really contribute to the class. So only the principal symbol of this operator determines the class. So we don't need to know the lower order part, we don't need to know the full symbol expansion, but just the principal symbol alone determines the class in KK theory. Okay, so one of the main tools in KK theory is the Kasparov product. So this is a pairing which takes a class in the KK of AB and a class in the KK theory of BC and maps it to a class in the KK theory of AC. So this is a very important tool, and it has some very nice properties. So in particular, it's associative, which is a very important property. And it's also very functorial in more or less every way you can think of. So it's contravariant in A, it's covariant in C, and it has many nice functorial properties. So what Kasparov did, Kasparov proved the existence of this pairing, but it doesn't mean it's always necessarily easy to construct this Kasparov product. So a very important step in this direction is the theorem by Koen and Skandalis. So here we consider 3 Kasparov modules. So we want to compute the Kasparov product of F1 with F2. And so the theorem also presumes given let's say a candidate for the Kasparov product, the operator F, which acts just on the tensor product of the 2 Hilbert modules. And then the theorem says that if you can check these 2 conditions, the connection condition and the positivity condition, then indeed this operator F represents the Kasparov product of F1 and F2. So these connection and positivity conditions, they more or less compare the operator F with both F1 and F2. So the connection condition compares F with F2. Yeah, very roughly speaking, it sort of says that F, if you restrict F to the E2 part, the second part in the tensor product here, then it has to be more or less comparable with F2. And in this talk, I will mostly focus on the positivity condition. So the positivity condition requires this commutator or anti-commutator of F1 with F to be positive modulo compact operators, or to be more precise, it doesn't have to be strictly greater than 0, but it can allow this minus kappa here as well. So as I said already, for pseudo-differential operators, compact operators, let's say these are the negative order pseudo-differential operators. So if F and F1 are both 0th order pseudo-differential operators, then their commutator is again a 0th order. So this is a condition on this 0th order commutator modulo negative order psi-dios. So again, this condition here depends only on the principal symbol of this commutator of F with F1. And the lower order part of this commutator is not really essential. And in fact, Koen and Skandalis proved a bit more than just what I wrote down here. So he not only said that if you find a candidate F which satisfies the condition, then it is the Kasparov product, but also that such an operator F always exists. Okay, so we can always find an operator F which satisfies these conditions and which then therefore represents the Kasparov product. Okay, so what I'd like to introduce next is the unbounded picture of KK theory. So one of the main motivations behind this unbounded picture is that it's more suitable to also describe geometry. So the class in KK theory of a Kasparov module is a very topological object. But now we are going to consider representatives, which are also suitable for describing geometry of these objects. So this geometry is not visible at the level of the equivalence class, but it's only visible at the level of the representatives. So first is the unbounded Kasparov modules were introduced by Bage and Jules already in the early 80s. And what I will talk about mostly today is a generalized version where the operators are no longer assumed to be self-joint, which was introduced by Hilsum. So the idea is similar as for a bounded Kasparov module. So again, we have a Hilbert module and the representation of our algebra on this Hilbert module. And the difference is that we now consider an unbounded operator D. So this is assumed to be symmetric. The regularity condition is an assumption we need for operators on Hilbert modules. For Hilbert spaces, we could just consider a closed operator, then the regularity is automatic. The first main assumption is that the resolvents are compact, so, or to be precise, locally compact. So once we multiply by an element in algebra, it becomes compact. And the second main assumption is the existence of a nice dense subalgebra. We can think of as the smooth subalgebra. So first of all, this algebra has to preserve the domain of D. What we assume now is something slightly stronger than we did. It also maps the domain of the adjoint of D, which is bigger than the domain of D, into the domain of D. And then importantly, the commutator of D with these elements is assumed to be bounded. And yeah, then let me mention, if in the special case where the operator D is self-adjoint, this is an unbounded Kasparov module as introduced by Baj and Zhu. And in the special case where the C-star algebra B is just the complex numbers, then E is just a Hilbert space, and then this is usually called a spectral triple. Okay, so again, we can consider the corresponding.
Koen, can I ask a small question?
Yes.
It's Ludwig. Hi, Koen.
Yeah, hello.
So A can be unit of C-star algebra, right? And A script can be also unital.
Yes.
So in this case, if
A script is unital, then this assumption that we have here is telling us that the domain of D star is contained in the domain of D,
okay.
And then the operator is self-adjoint.
Okay, thanks.
So this non-self-adjointness is really mostly relevant in the non-unital case. Yeah.
Okay, thanks.
Okay, so we can again associate a class in KK theory to such half-closed modules. So what we do is we take the bounded transform of the unbounded operator. And then it was proved by Baj and Zhu in the self-adjoint case, and he also showed it still works in this non-self-adjoint case, that the bounded transform defines the Kasparov module. And then we can take the equivalence class in the KK theory of this bounded transform. And then, so we just define the class of a half-closed module to be the class of its bounded transform. So here, the typical example is not zeroth order pseudo-differential operators, but now the typical example will be a first order differential operator. So to be precise, an elliptic first order differential operator. So let's write down a very specific example. We can consider the smooth manifold given by the unit interval. So consider the open unit interval. So the C-star algebra A is then just continuous functions on this interval which vanish on the boundary. We consider a dense subalgebra of compactly supported functions which are smooth. So this is a dense subalgebra. This acts on the Hilbert space of L2 functions on the unit interval. And then we have our operator on the unit interval, which we take to be just the usual derivative operator. Okay, so this is a half-closed module. So the representation, this star homomorphism that we have here, just pointwise multiplication. The compactness of the resolvent is due to the ellipticity of this differential operator. The boundaries of this commutator, of course, because if you take a commutator with a first order operator, this is like differentiating the function A, and we assume A to be differentiable, so in fact even smooth. So this derivative is bounded. And here for this domain inclusion, so the differential operator we consider is initially defined on the domain of smooth compactly supported elements in the unit interval. So because we consider the open unit interval, these are compactly supported in the interior. So in particular, these elements which vanish on the boundary. So then the D is the closure of this operator, so we consider the minimal extension. The adjoint of D will then be the maximal extensions. These are so the elements in the domain of D star are allowed to have arbitrary values at the boundary. But now if we multiply by a function A, which is compactly supported, then in particular, this function vanishes at the boundary. So the product vanishes at the boundary and we end up in the domain of D. Okay, so this works. And we have a nice half-closed module. We can also consider a similar example in the self-join case. So we just consider the more or less the same differential operator, but now put it on the whole real line. So we consider compactly supported smooth functions on the real line, L2 functions on the real line, and just the usual derivative on the real line. Okay, so this works in the same way. The main difference is now that this is self-joined, and this basically reflects the fact that the real line is complete. So the unit interval on the real line, they are diffeomorphic spaces. So in the sense, they are topologically the same. So in particular, the algebras, the C-star algebras of functions on these spaces are isomorphic. So we can identify these C-star algebras, and then we can also identify the corresponding KK groups, or the K homology groups in this case. And then what we find is that the class of this operator on the real line, if we identify the real line with the unit interval, then this is the same as the class of the operator on the unit interval. So topologically, these two triples describe the same thing. But of course, then the main point here is that geometrically, they are rather different. So the unit interval with the standard metric is very different from the real line with the standard metric. So one is complete, the other is incomplete. So the idea of this unbounded picture of KK theory is really that we also care about the geometry. So we don't just want to consider objects up to equivalence in the bounded picture, but we want to preserve that geometric information. And so in particular, this means that if we are given the geometry of the unit interval, then we are not allowed to just pretend that it's the real line and make it complete, but we would like to just stick with the given geometry of the unit interval. And in this case, in particular, this forces us to consider non-self-adjoint operators, because this differential operator here on the unit interval is not self-adjoint, and it is not even a way to make it self-adjoint because it doesn't have any self-adjoint extensions. So we really have to accept that this operator is non-self-adjoint and work with the more general version of half-closed modules.
Sorry,
wait a second,
does have
because
self-adjoint extensions.
when you say that it doesn't have self-adjoint extension, this is not true, because if you take periodic boundary condition, this is a self-adjoint extension.
Yeah, no, okay, sorry, I think you're right, yeah.
Yeah.
No, if you have one open endpoint, I think it will probably work. So,
No,
yeah,
but I mean,
on the half
as it
line.
is, it has
You're right,
plenty
yes.
of self-adjoint extension, because
Yes, it does.
if efficiency indices are equal to 1, they are both equal.
Yeah. No, you're right. Yes, sorry. Okay, so this is the unbounded picture of KK theory. So then the question is, can we describe also the Kasparov product in this unbounded picture? So I just showed you this theorem by Koen and Scandales for how we can describe this in the bounded picture. And then Kucerovsky provided us with a similar theorem in the unbounded picture. So again, we consider 3 triples. So we want to compute the Kasparov product of D1 with D2. So this theorem of Kucerovsky only applies to unbounded Kasparov modules. So this is the self-adjoint version of the unbounded picture. And then again, as in Koen and Scandales, we have this candidate for what we think the Kasparov product might be. And then we have 2 conditions, which if we can check that these conditions are satisfied, then this candidate indeed represents the Kasparov product. So this first condition, the connection condition, is very similar to the Koen-Scandales connection condition, just with unbounded operators. And now this commutator is not assumed to be compact, but it has to be bounded. And for today's talk, most important is the positivity condition. So the Koen-Scandales positivity was formulated in terms of a commutator or an anti-commutator. Here in the unbounded picture, we have to be a bit careful because now we deal with unbounded operators. It's not clear if this commutator is well defined. So the composition of 2 unbounded operators might not be densely defined. So for this, it's more convenient to rewrite this condition, and instead of writing down the commutator, we write it down in the form of this quadratic form here. So still, we need to be a bit careful with the domain. So we assume that the domain of D is contained in the domain of D1, so that both D1 and D are well defined on this vector psi. And now here we assume that this commutator form, let's say, is bounded from below. So let's briefly compare this with what Koen and Skandalis did. So positivity condition from Koen and Skandalis. If I paraphrase this a little bit, it roughly requires this commutator between f and f1 to be positive. And in the context of pseudo-differential operators, let's say positive modulo negative order pseudo-differential operators, roughly speaking. So if you compare this with Kucerovsky's positivity condition, so let's pretend there's no domain issue and we just write down the commutator of D1 with D. Then Kucerovsky requires this commutator to be positive. And here on the right-hand side, we just have something bounded. So this is positive modulo bounded operators. And let's say in the context of differential operator, this means positive modulo zeroth order operators. Okay, so what we see here is that, as I mentioned before, in the Koen-Skandalis version, this condition depends only on the principal symbol of this commutator. But here in Kucerovsky's version, if you have D and D1 both being first order differential operators, then in general, this commutator can be a second order differential operator. And now we have a condition modulo zeroth order operators. So this not only depends on the principal symbol of this commutator, but also on the first order part. So this is a bit less natural than in the Koen-Skandalis version, where we really have to worry about what the lower order part of the symbol does in order to check this condition. So that's one little issue with this Kucerovsky's condition. And a second thing, what we had in the Koen-Skandalis condition is not really this commutator is positive modulo compact operators, but we can sandwich this commutator between elements in the algebra, which I think of as localizing this condition. So again, if A is, for instance, a compactly supported function, then sandwiching the commutator between A and A star is sort of restricting this commutator to the compact support of A. So this is saying that in Koen-Skandalis, we only need to check this condition locally on every compact subset. And of course, checking a local condition can be easier than checking a global condition. So again, if the algebra is unital, there's no really any difference between local and global versions. But for non-unital C-star algebras, this can make a big difference. Okay, so these are two issues with Kucerovsky's version of the positivity condition that we would like to resolve. So first of all, that it depends on the sub-principal symbol of this commutator. And second, that it imposes a global condition instead of only a local condition. Okay, so what I want to spend the rest of my talk on is to describe how this positivity condition can be adapted in order to solve these two issues. Yeah, so let me mention, I don't want to sound too negative about Kucerovsky's condition. So of course, it is a very useful theorem, and it has been used a lot in the literature on the unbounded Kasparov product. So it's one of the cornerstones underlying the construction of the unbounded Kasparov product. So it is a very useful theorem. But these two issues show that there's still room for improvement. So we would like to be able to apply this theorem in more general certain circumstances. For instance, to this simple example of, to a simple example that I'll write down in a moment. So this mention also that this solving the second problem, this making the condition local instead of global. This also allows us to consider non-self-adjoint operators. So this means we can consider half-closed modules just as easily as unbounded Kasparov modules. So the idea there is more or less that if we say we have a compact subset of our unit interval, for instance, then we can consider our operator on the unit interval and restrict it to this compact subset, or we can consider the operator on the real line and restrict it to this compact subset. And once we restrict this to the compact subset, you can no longer tell the difference. So what we have here is that the operator on the unit interval is not self-adjoint, the operator on the real line is self-adjoint. But as soon as we restrict to the compact subsets, we can no longer tell the difference. So locally, there's not really any difference between self-adjoint and non-self-adjoint operators. The difference really appears at infinity or at the boundary of the manifold. So as soon as we localize this, this difference disappears, and we might as well consider non-self-adjoint operators. Okay, so the way I'm presenting it here sort of seems like this possibility of considering the non-self-adjoint case comes as a byproduct of localizing, but in fact, the motivation is more like the other way around. So one of the main reasons why we want to localize the positivity condition is to make sure that we can also consider non-self-adjoint operators. And I should also mention I'm not the first to consider this idea. So there's some work by Jens Kaat and Walter van Zuilenkom, who have already worked on generalizing this Kucerovsky's theorem to allow for half-closed modules as well. So what I'm presenting here is sort of building further upon their work. Okay, so let me describe one little simple example of which does not, where Kucerovsky's theorem does not apply, but where we would like to be able to apply this theorem. So what we consider here is the unit square. So there's two copies of the unit interval. So algebra A will be the functions on this unit square, B is the functions on the unit interval, and the algebra C is just the complex numbers. So the picture more or less looks like this. So we have our unit square. So this is our manifold M. So let's say we have an x coordinate here and a y coordinate. So we have, let's say, an x and a y coordinate. And what we consider is a submersion of the unit square onto the unit interval. So we can map this unit square onto the x coordinate. So then the fibers of the submersion are just these vertical lines. And so we consider two operators, d1 and d2. So d2 is the example I already mentioned, just the derivative on the unit interval. So this is in the x coordinate. And d1 is a family of vertical differential operators. So the family is parameterized by x, and this family differentiates along the y coordinate. And now, so the operator d1 defines a KK class in the KK theory of A and B, and the operator d2 in the KK theory of B and the complex numbers. And we would like to compute their Kasparov product. Okay, so we know what this Kasparov product is supposed to look like. So it's this operator D. So roughly speaking, we just take the sum of d1 and d2. Just have this sigma 1, sigma 2 there. These are Pauli matrices. So this is because we start with all dimensional manifolds and we construct an even dimensional operator. So we have to allow some space for Z2 gradings. But if you ignore that, this is roughly speaking just the sum of d1 and d2. This is the Kasparov product, but Kucerovsky's condition fails for this operator. So Kucerovsky's positivity condition is sort of a condition on the commutator of D with D1. So the commutator or anti-commutator of D1 with itself is not really the issue, but the issue comes from the commutator of D1 with D2. So if we try to compute this, so d2 is just the derivative operator in the x direction, so it doesn't commute with this function of x. What it does is it computes the derivative of that function. So what we get, if you compute the derivative, is this factor 1 over x squared out front. So the issue here is that this function is no longer bounded. So of course, it is locally bounded, but it's not globally bounded on the whole unit interval. And worse than that is it can also not be relatively bounded by any of these operators d1, d2, or d. So it's really a new unbounded operator, which makes Kucerovsky's positivity condition fail in this instance. And so we kind of see all three problems that I mentioned at the start here. So first of all, these are of course non-self-adjoint operators because we have incomplete manifolds. And problem number one, so we see here this commutator a priori it would be a second order operator. In this case, it's only a zeroth order operator. So the first order part is even fine because it's zero, but the zeroth order part of this operator causes trouble because it is unbounded on the unit interval. And second, we see that the problem is here is really that Kucerovsky's condition is global instead of local. So if we restrict this function to a compact subset, then of course on any compact subset it will be a bounded function, and then there's no problem anymore. But the problem is really that this Kucerovsky condition is a global condition, and globally this function is not bounded. Okay, so I want to spend the rest of the talk to explain how to adapt Kucerovsky condition and to avoid these issues. So first I will focus on condition one, so this dependence on the subprinciple symbol. So this we can solve as follows. So what I show here is basically the same, more or less the same theorem as what Kucerovsky proved, except that we add an extra factor in the positivity condition. So Kucerovsky just had the right-hand side being bounded by -c times psi inner product with itself. Now we put this extra unbounded operator in the inner product on the right-hand side. So what does this mean? Again, let me paraphrase this in terms of condition on the commutator. Basically, we're now asking this to be positive modulo first order operators. All right, so in the abstract setting, this means first order with respect to the scale given by this unbounded operator D. So in the case of differential operators, at least if you, let's say, consider compact manifolds where you don't have to worry about coefficients blowing up, then this indeed means that this commutator is relatively bounded by the elliptic operator D, and therefore it must be a first order differential operator. So now we have a condition which really depends only on the principal symbol of this commutator, namely on the second order part of this commutator, which is exactly what we wanted. Okay, so for the proof of this theorem, I don't want to say too much about the details, but the idea is the same as in the proof of Kucerovsky's theorem. So of course, the obvious thing we want to do is to use these connection and positivity conditions for the unbounded operator to try to check the connection and positivity conditions of the Koen-Skandalis theorem. So the connection condition I haven't changed. This works in the same way. The positivity condition, it follows more or less the same strategy as Kucerovsky, but the difference is that we have to be a bit more careful with our estimates. We have to make sure that this weaker version of the positivity condition still suffices to check the Koen-Skandalis positivity for the bounded transforms. And so if we are careful enough with our estimates and the estimates are sharp enough, then indeed we can prove this. Okay, so this resolves the first issue that I mentioned about Kucerovsky's theorem. So the rest of my talk, I would like to discuss the second issue. So this is how to make the positivity condition local instead of global.
Koen, can I ask again?
Yeah.
So this is just for the example or in general, or if D has higher order differential operator, it still works?
This works in general, I guess. So
Okay.
just with the conditions that I wrote down here. So if you have arbitrary, let's say, unbounded Kasparov modules, so you have to satisfy the good definitions of an unbounded Kasparov module. So I mean, this intuitively kind of forces it to be a first order operator because you need bounded commutators with algebra.
Okay.
But yeah, this works in the general abstract context. Yeah.
Okay. Thanks.
Koen, could you comment on the plus sign? That is because in this positivity condition, if it were a minus sign, I could understand a commutator.
Okay, so yeah, so the left-hand side, it's more like an anti-commutator. So
Yeah.
I'm sort of swiping the Z2 gradings under the rug here mostly, but these operators D and D1, they are odd with respect to some Z2 grading. So when I say commutator, I always mean the graded commutator. And for all operators, the graded commutator is the anti-commutator.
Okay, thanks.
So this here really means the anti-commutator of D with D1, and that is this plus sign, yeah. Okay, so let's try to localize this positivity condition. So let's start with a half-closed module. For convenience, we assume the representation of this module to be essential. And the main assumption I will impose is that in the dense subalgebra A, we assume that we are given a nice approximate unit, which is almost idempotent. So this means that un plus 1 times un is equal to un. So if you think of A to be functions on a manifold, for instance, then you can get such an approximate unit by considering an exhaustion of your manifold by compact subsets. So then each function un is a function which is constant equal to 1 on some compact subset and which vanishes outside of a bigger compact subset. And from some such functions, you can then construct such an almost idempotent approximate unit. In the general case, so if A is in general a separable C-star algebra, it's good to realize that the C-star algebra always contains such an almost idempotent approximate unit. So this is not an assumption on the C-star algebra, but it is an assumption on the dense subalgebra. So we assume here that this almost idempotent approximate unit is contained in our dense subalgebra of differentiable elements. So it's not clear if this is always true in any dense subalgebra. Okay, so given such an approximate unit, we can construct a corresponding partition of unity. So just starting at 0, we define K0 to be the square root of U0. And for all higher K, we take the difference between two elements and the square root of that. So this is constructed in such a way that if we sum up from K0 to n, and we sum up the squares of K, then this will just give us un. So in particular, un converges to the identity strongly. So this means that if we take the limit of this sum going to infinity, then we have this strongly converges to the identity. So this justifies the use of the term partition of unity. Okay, so we're going to use these to localize our operators. So we start with our operator D, the possibly non-self-adjoint operator from our half-closed module. And we sandwich it between the two elements of this approximate unit. And we call this operator dk. And then it is known that this operator is going to be regular and self-adjoint. So even if D is not self-adjoint, this localization will be self-adjoint. And since D is regular, this localization will also again be regular. And then from these localizations, these localized operators, we're going to construct what I call a localized representative of the KK class. So we pick any sequence alpha k of positive numbers. And what we do is we first rescale our operator dk by this positive number alpha k. Then we take the bounded transform of this rescaled localized operator. And then we batch together all these bounded transforms using our partition of unity. So we take an infinite sum here. So this sum is strongly convergent. So it gives us a well-defined operator. And the main reason why we introduce these positive numbers alpha k. So in the end, we want to use this localized representative to check the positivity condition of cons candales. So the strategy there will be to first prove estimates for these for each term in the sum. So prove local estimates for each of these localized representatives. And then we want to sum these up to get a global estimate. But the problem is if you find, we can find an estimate for each k, but in general, these the constants appearing in this estimate will not be uniform in k. So this is where this trick appears using alpha k. So for each k, we can rescale this operator And then correspondingly, we are rescaling the constant in the estimate. So we can always choose an alpha k such that these estimates become uniform in k. And then we can sum these up and get a global estimate for the localized representative. So this trick here by this local rescaling was also used by Jens Kater and Walter van Zuilenkom in their work. So it's really important that we can rescale each localized operator independently in this sum to get uniform estimates.
Excuse
me,
when you say rescale, I mean, in which direction you rescale? Infinity or zero?
0, I think.
0.
Yeah, so we want the constants appearing in the estimates to be small enough.
I see. So in fact, this means that you increase the metric, if I understand correctly.
Sorry?
You enlarge the metric.
Yeah, I guess so, yeah.
Okay.
Okay, so then what we can check is, first of all, that this localized representative gives us a bounded Kasparov module. And second, that the class it represents is the same as the usual class of the bounded transform of D. So it represents the same class in KK theory. So roughly the idea here, so as I mentioned, to define the same class in KK theory, it's enough to have a locally compact perturbation. So we can check that these two operators are in fact locally compact perturbations of each other. So roughly the idea is that if you take the difference between the localized operator, so the bounded transform of the localized operator and the bounded transform of D, then at least on the support of KK, this difference is going to be compact. And similarly, so this is really reflecting that this localized operator on the support of KK is basically the same operator. And then you can check that for the bounded transforms, this means that you only get a compact difference. And similarly, this rescaling by alpha k also does not affect the KK class. So the difference between the bounded transform of dk and its rescaled version is also going to be locally compact.
Yeah, let me just comment on that. I mean, so what is the case really is that, you know, the bounded form is really only judging the conformal structure. And when you rescale, you are not changing the conformal structure. So what you are doing essentially is putting in a Weil factor in the story to compensate for that. Yeah.
Yeah.
Well, and but let me add one thing, which is that there is a more geometric way of formulating a Weil factor, which is to multiply D on both sides by the same positive operator.
Yeah, so that maybe that might be an
interesting
alternative approach. So instead of taking this infinite sum with constants, we might just take one function or something. And
yeah, so what I mean is that it would be nice if you want to restate the formula by changing simply D by multiplying on both sides by a rho, which is a Weil factor, and which would achieve exactly the same thing, I think. Yes.
Yeah. Yeah, then that might work as well. Yeah. Yeah, it's okay. So with these two compact perturbations, if we now consider the difference between our localized representative and the bounded transform, then this will also be a locally compact perturbation. So we put UN in front here. So with the UN, by construction, basically, there are only finitely many KK which are non-zero on the support of UN. So if you put a UN in front of this localized representative, then this infinite sum becomes a finite sum. So then here we have a finite sum, a finite number of compact perturbations, which is again a compact perturbation. Okay, so this is our localized representative. So now let's look at localizing the positivity condition. So so we start with 3 half-closed modules. So we want to compute the Kasparov product of D1 and D2, and we have our candidate for the Kasparov product, which is D. Again, we assume this existence of this approximate unit. And then we define a local version of the positivity condition as follows. So first of all, it's local in the sense that everywhere I put this approximate unit in the inner product. So I don't apply these operators globally on the domain of D, but I always localize this element xi in the domain of D to the support of UN, and then I consider the condition there on the support of UN. So this is just the localization step. And then the second step is I've strengthened this local positivity condition a little bit. So there's this, what I then called a strong version of the local positivity condition, which adds this additional term in the right-hand side of the estimate. And it's important here that this constant UN is strictly positive. So being 0 is not good enough. We need to have a strictly positive constant here. Yeah, so why do I need this strengthening? Well, without going into too much details, let's just say it's there because I needed to make the proof work. So without this additional term, I have not managed to prove the version of Kucerovsky's theorem that I would like. So I've added this strengthened version of the local positivity condition to make it work. This is not the only way to make it work. So in the paper that's on the archive, there's also another version, which is more motivated by the motivating example of differential operators on smooth manifolds. So of course, on a smooth manifold, let's say this approximate unit can be assumed to be smooth as well. And in fact, I can formulate a proof where what I need is more or less that these approximate units are at least twice differentiable. So if you have some suitable notion of twice differentiability, then it's also possible to prove a version of Kucerovsky's theorem. But this twice differentiability, I mean, it's very natural on smooth manifolds. I find it a bit less natural in the abstract context, where in general, for an unbounded Kasparov module or a half-course module, you only have boundedness of a single commutator with elements in the algebra. And I prefer not to restrict this Kucerovsky's theorem to having to impose additional regularity in the definition. So I prefer this one, and one advantage of this strengthening here is that it's quite naturally satisfied in the constructive approach for the unbounded Kasparov product. So I will come back to that a bit later. But yeah, I would say that in the constructive approach is having this additional term here is quite natural to obtain this estimate.
Koen, can I ask a quick question?
Yeah.
You want this minus a half to be a plus a half, I guess.
Ah, yes. Sorry, I do. Thank you.
Yeah,
no,
so
that's good.
Yeah, it's just a minus. It's probably just a typo, but
yes, it is. Yeah, so it should be the same. That's
good. And this, sorry, and the Cn, is that the same as the C in the statement?
Yes, that's also a typo. Thank you.
Okay.
But, this should depend on n, the C. Yeah.
Okay.
Yeah. So the second term on the right hand side should be the same as in the previous theorem, just localized. Yeah.
Thanks.
Okay. So then, with this condition, we can formulate a version of Kucerovsky's theorem. So now. We are no longer restricted to the self-joint case, but we can consider half-closed modules. We assume the same connection condition as in Kucerovsky's theorem. So this connection condition works in the same way as in the self-joint case. And the difference is that we now consider the existence of this approximate unit, and we require that the strong local positivity condition is satisfied. And with these conditions, we can again prove the same statement as Kucerovsky did. So this operator D indeed satisfies the Kasparov product of D1 and D2. So let me briefly sketch the idea of the proof.
Sorry, can I ask about something right now? It's just that, so we had this, Walter and I proved also a theorem about looking a little bit similar,
yes,
but I was wondering whether this is contained in your theorem or are they just disjoint? Is our theorem a spatial case of yours, or?
Yeah, so at least in the theorem I'm presenting here, because of this strong in front of the local positivity condition, this you do not assume in your theorem, I guess.
But also this almost idempotent approximate unit. I'm also confused with that one.
Yeah, so maybe I'm a bit more specific than what you do in your theorem. So you have something similar. I mean, you don't have an approximate unit maybe, but you have this this localizing subset, you call it, I think. Where the approximate units that I would consider would be a special case of your localizing subset. So I'm being a bit more specific in my assumptions, I guess. Yeah.
Okay.
Can I ask this again?
Yeah.
Is that really the case? Because if I remember well from the localizing subset of Walter and Jens, that was supposed to commute with one of the unbounded operators. Whereas your almost idempotent approximate unit does not, I think.
Yeah, no, that's true. That's a you're right. So it's not really there's a bit of feedback, I think. Yeah, so this in that sense, my assumptions are weaker. Yeah, so I mean
there is a. Yeah.
I think if you look at it very precisely at the details, neither one is contained in the other. There is a lot of overlap between the two, but they're not. It's not strictly a generalization. Let's say, I think. But okay, let me briefly sketch the main steps in the proof. So step one. So basically the idea is that we assume this strong local positivity condition for our original operators D and D1. And the first thing you want to do is to check that we get a similar local positivity condition for the localized operators. So for dk and d1k, so both d and d1 localized to some compact subset. And then once you have this for the localized operators, you want to check Koen-Skandales positivity condition for the bounded transforms of these localized operators. So to be precise, we fix some constant kappa, which we have in the condition of Koen-Skandales. And then for every k, we show that there exists a positive number alpha k, such that we have, roughly speaking, the Koen-Skandales positivity condition on the support of chi k. So we have the commutator of the bounded transform of dk with the bounded transform of d1k. Sorry. So it's important that we rescale this d1 by our positive constant alpha k. And then we can produce this estimate that this is bounded from below by kappa times chi k squared. And this is true modulo compact operators. Right, so this rescaling by alpha k is to ensure that this constant kappa here can be achieved independently of k. And then the second step is, once we have these local estimates, we want to check that the Koen-Skandales positivity condition holds globally. And to be precise, it should hold globally for just the bounded transform of D and for the localized representative of D1. So what we get, so now we take this commutator of FD with the localized representative of D1. So as I explained before, you can, up to compact or locally compact perturbations, we can write this in terms of the bounded transforms of the localized representatives. Again, modular compact operators. And then we can apply the estimates from step 1. So for each k, we have this estimate. And now again, because of the UN in front of this, there are only finite many k which are non-zero on the support of UN. So this sum becomes finite. So we have this estimate for a finite number of terms. And then we sum over the k squared. But this is a partition of unity, so this sum will be 1. So we're left with only the UN squared. Okay, so this roughly sums up the proof. So the technical heart of the proof, I would say, is this step 1. So you really have to show that this local version of the positivity condition implies the Cons-Kandales positivity condition locally. Okay, so this is my localized version of the Kucerovsky theorem. The last thing I want to mention is, as I said, this strengthening of the local positivity condition is quite naturally satisfied in the constructive approach to the unbounded Kasparov product. So let me just very briefly discuss that in the last few minutes. So the idea is more or less that we want to construct our candidate. So we want to compute the Kasparov product of D1 and D2, but instead of obtaining D as given, we want to construct it somehow. So I'm not actually going to do this construction. I'm sort of specializing to the case where we just need to somehow construct this operator T. So I'm going to consider my candidate for the Kasparov product to be of the form S plus T, where S is simply obtained by tensoring the D1 with the identity operator. And what remains to be constructed then would be this operator T. So typically, what you would construct is an operator T of the form 1 tensor D2, except this is not well defined, so you have to twist by some connection. So really the difficult part is to find a connection and construct this operator, and in particular construct this operator in such a way that these assumptions here are satisfied. That's what makes it difficult. So in particular, we want this operator D to be a half-closed module. So for instance, you have to prove regularity of D, and this can be far from obvious. Yeah, so let me mention that the connection condition in Kucerovsky's theorem is guaranteed by this assumption A2. So here in A2, we assume basically the connection condition for this operator T, and we don't have to assume it for the operator S because this follows more or less automatically. Namely, if we just, not even a commutator, but if we just take the composition of S with T psi, this is just tensoring on D1 psi, and this is a bounded operator on E2, provided we take psi to be in the domain of D1. And in this connection condition, it suffices to take a dense subset. So that's good enough. So for this S part of the operator T, the connection condition is satisfied more or less automatically. What you need to do is construct this operator T for which this connection condition is satisfied. Okay, so what remains to be done is to guarantee that also the positivity condition is satisfied. So for this, we do the following. So we have the same setting as on the previous slide. Consider these operators S and T. We assume that these assumptions I just wrote down are satisfied. And then we want to guarantee that also the positivity condition is satisfied. So now this positivity condition is basically a condition on the commutator or anti-commutator of D with S. So D is now some S plus T, so the anti-commutator of S with itself is all right. That's not the issue. But what we need to control is the operator of T with S. And so in unbounded operators, we first of all have to make sure that this commutator is somehow well defined. So we consider a core in the domain of D. And we assume that at least if we restrict to the support of UN, then this core is contained in both the domain of ST and the domain of TS. So in particular, the commutator of S and T is well defined on this core, at least locally. And second, once this commutator is well defined, we are going to assume the following upper bound. So we want this commutator to be relatively bounded by the operator D. So this is really telling us that this commutator of S with T is a first order operator. So again, if S and T are both first order differential operators, their commutator will be second order in general. So we're assuming that it is now in fact first order. So basically this means that the second order part of this operator must vanish. And for differential operators, this more or less means that the principal symbols of S and T have to anti-commute, so that the principal symbol of the commutator or anti-commutator vanishes. Okay, and then with these assumptions, we can again show that this operator D represents the Kasparov product. So the proof ID, we just briefly sketch. So we need to check if the positivity condition, we need to look at this commutator of D with S. So the anti-commutator of S with itself is just 2S squared. And what we're left with is the commutator of S with T. So now, because of our assumptions, this commutator of S with T is first order. So roughly speaking, we can say this is at least bounded from below by this constant Cn times this first order operator. And what we have on the right-hand side here is exactly what we want for the strong local positivity condition. So the second term is just saying it's bounded modulo first order operators, so positive modulo first order operators. And then we had this strengthening of the local positivity condition with this operator S squared. So in particular, we do obtain this strengthening and we in fact obtain it uniformly. So we can take this constant U n in the strong local positivity condition. We can take them be equal to 2 for all n. So in particular, this strengthening of the local positivity condition is quite naturally obtained in this constructive approach. Really, all we need to ensure is that the commutator of S and T is first order at most. Okay, so as I mentioned, I'm not actually given the construction of the unbounded Kasparov product, but if you come up with a construction, then I think this is a very useful way of checking that it indeed represents the Kasparov product. Okay, so with that, I've reached the end of my talk. So let me just show you the main references that I mentioned, and thank you for your attention.
All right, thanks, Koen. I forgive you for taking these few minutes.
Thank you.
Any questions or comments?
I have one general question. Because after all, you know, to really obtain the unbounded analog of the theorem that we had with Candalis, it would be, of course, very important to also obtain the existence. Now, so I mean, I don't know what is the situation for the existence of the.
Yeah, I mean, it's still an open question. So there's no general existence given.
I see.
B1
okay, so let me make again a guess. Let me make a guess for the existence. My guess is the following. You see, because the bounded part essentially captures the conformal structure, my guess would be the following: that in order to get the existence, one should be allowed to change by a Weil factor the two operators, namely to replace the first operator by ρ d ρ, where ρ is a Weil factor, and similarly for the second. And then I would believe that the existence should be available in general.
Mhm.
That's my guess, if you want. Because I mean, conceptually, this is exactly what happens, in the sense that, okay, in the result with Scandalis, we sort of establish the existence. So if you want, at the level of the, so in fact, one could start from there, and the fact that you are already given some kind of metric in both cases, and sort of amplify the metrics using Weil factors to get the existence from there. I think it's quite important to settle the existence problem, because otherwise, you know, it's kind of,
Yeah,
I
so
mean,
you have
it's
to
very
find
nice when you have candidates where, of course, you can go. But I mean, the proof that you showed where you were localizing and so on really indicates that you are using the freedom of Weil factors. And that
So for this localized representative, you really have to sort of push the boundary to infinity in a sense,
Yeah.
So for this existence problem, I mean, you have to optimize somehow. So of course, we know existence modulo homotopy equivalence. So
of course,
you can go by the
but yeah,
and
but
we do
what
have
I mean,
existence if you do not change the geometry whatsoever. So you have to find the optimal middle ground where you change the geometry maybe a little bit, not too much. And this is
exactly.
finding the right
I mean,
middle ground.
my point is the following: is, in fact, you know, I introduced the unbounded situation at the very beginning of the 80s for defining the geometry, and then okay, Baj and Julke developed the unbounded theory, but in general. But I mean, in the case of cohomology, I mean, you know, it was from the start to have the geometry, and then I mean, there is this very important nuance that the bounded situation describes really the conformal structure, and the supplement that you get from the unbounded theory is really the Weil factor, of course, which is essential in order to do Riemannian type geometry. But there, I think there is really the most important question for me is existence in general. I think, you know, this is a very sort of crucial problem that should.
Yeah, no, I agree. It's an important problem, and so I'm not answering the problem, but I'm hoping that what I showed you today might help in that direction.
Yeah. Can I comment slightly on this? It's so this passage. I don't know exactly what you intend that rho should be. But I mean, when you, in the non-commutative setting, if you pass from D to an operator of the type rho D rho, I think it's unlikely that you get bounded commutators with the
No, but you have to twist, of course. You have to twist, of course.
Yeah, okay. Yeah, so then it's...
Of course, you are now in the realm of the twisted spectral triples, of course, in the unbounded case. So if you want, this is a very telling thing, because what it will show is that probably the unbounded theory as such is not really suitable, and it has to be twisted in a suitable way. I mean, this is what I have in mind.
So there are there are some examples.
My point is that when you have a twisted spectral triple unbounded, then the bounded form is an ordinary spectral triple. So I mean, this is the point. That's the whole point.
Yeah. But sometimes, I mean, I think there's a problem with twisting also, that sometimes you will need to twist different legs of your.
Well, okay. Well, that's perfectly fine also, because in fact, I mean, if you want the real theory that nobody has much idea about is a theory where the twist is not by a single thing.
Yeah,
I mean,
exactly. Okay.
And, for instance, if you want to learn about this, I mean, there is this paper which I wrote with Farzad Fatizadeh on the non-commutative torus of dimension 4, which is obtained by doing the product of two conformal structures, so that when which have different Weil factors, so that when you make their product, it's no longer conformal to the ordinary conformal structure. And then what you have is the twisting, if you want. So the twisting is like the modular theory, but it is a modular theory which is much more involved, because in general it will involve something like GLN. I mean, it will involve the Jacobian in full form, and not only the determinant of the Jacobian. So I think, you know, of course, this is extremely important, because, I mean, when you consider foliations, you are confronted. I mean, if you look at the 83 paper about transverse fundamental class, I mean, you are confronted from the start, in the case of foliation, with a transverse structure which is twisted, but twisted by GLN, if you want, not only just by the determinant. So I mean, you know, this is a core problem of non-commutative geometry. Really, I think it's very interesting to dig more and more and to find things. Okay, you know, and to experiment. I mean, the most important thing is to experiment, I would say. Yeah.
And maybe to add a comment to this, I mean, so because this was mentioned before, so the difference or the kind of the similarity between what Koen was showing and what I did with Jens before.
Yeah.
I think if you kind of resolve that, I mean, what we did was much more in that vein that you kind of you take something like rho d rho or x d x star, which is very much in that of that type. But then we had to give in on another condition, which was involving the vertical part essentially, this d1, which then Koen resolves in this kind of different setup. But then, so maybe a concrete question to Koen. I mean, do you get like twisted commutators, or is it somehow, is this approximate unit central? That's what you assume?
No, it's not assumed to be central. So I don't, and I kind of only use this approximate unit, I guess, to construct the localized bounded transforms.
So you don't consider a new kind of
but this localized operator doesn't need to have bounded commutators with algebra. I just I take the bounded transform and then it has compact commutators with algebra, and that still works. But this is also what Alain was saying. In the bounded picture, the twisting sort of disappears and you have an ordinary Kasparov module.
Yes. I also have some technical thing which might be useful. Apparently, you are considering quadratic forms which are lower bounded. And I mean, there is a very interesting paper of Barry Simon on unbounded quadratic forms, which you might have some use about. Where if you want the main property, in fact, it's a result which is due to Kato. But when you consider unbounded quadratic forms, you don't have to worry so much, in fact, about problems of domain and so on. I mean, the main property of the quadratic form which is being used is that it is lower semi-continuous for the norm topology. So what Kato did was to extend these quadratic forms, which are only densely defined, by putting them equal to plus infinity when they are not defined. And then what you find out is that it's an amazingly clear setup, because you don't have to worry about problems of domain anymore, because you know it's really a map to the zero infinity, where infinity is included. And the main property of this map, which actually sort of refers to the fact that it was a closed operator, is the fact that it is a lower semi-continuous. So it's a paper of Barry Simon, which is quite difficult to find because it's in the 70s, and it was published in the proceedings of the Edinburgh Society or something like that. So I mean, it's difficult to find, but it's extremely useful technically. I mean, it's of course, you know, it's because what I saw is that when you were writing the positivity condition, it was really exactly these quadratic forms, unbounded quadratic forms, which are involved. And which are normally a pain to deal with. But I mean, with this addition, which is in fact due to Kato at the first.
Yeah, okay, I'll try to look this up,
Yeah, it becomes much, much clearer, much better, yeah.
All right.
Can I ask still, Ludwig, hi. Koen, can you achieve the same results if you use real spectral triples and you use your rows functions, let's say, from the J algebra, so in the commutant algebra?
Yeah, I haven't really explicitly looked at the real case, but I think it should more or less follow through. Yeah, I wouldn't expect any difficulties if you have an additional real structure. But I
in this case,
no.
This case would be bounded commutators, usually commutators bound.
Yeah, so I would expect no problems, but okay, I didn't check.
It's not so clear what the definition is, right? I mean, for the bivariant case, what it means to be a real structure on an unbounded Kasparov module. Is that clear?
Well, it shouldn't be too hard to.
No, that should work, I think. Yeah.
Okay.
I think the bimodule structure should stay in the commutant of the other action, so that should be fine. you have a kind of tri-module.
Yeah.
Yes. Yes. Right. Yeah.
All right. If there are no more questions or comments, then we thank Koen again.
Yeah, thank you.
And we see each other next week again. So have a nice day.
Yes, thank you. See you next time.
Bye-bye.